You think sound travels through the air, like a bullet, like water through a pipe. You imagine it moving from here to there, crossing the distance between my mouth and your ear. That's what they told you in school, right? Sound waves propagate through a medium. Fine. But here's what bothers me about that explanation. It doesn't tell you what's actually happening. It just renames the mystery. Sound doesn't travel. Nothing moves from here to there. And when you understand what's really going on, when you see past the comfortable lie we tell students, you realize we've been describing one of the most extraordinary phenomena in nature using the wrong metaphor entirely. Let me show you what I mean. Here's an experiment. Simple one. Take a tuning fork, strike it against something hard, hold it near your ear. You hear a tone, pure, clean, sustained. Now, what just happened? The standard answer is that the tuning fork created sound waves that traveled through the air and reached your ear. Sounds reasonable, sounds obvious, wrong. The tuning fork didn't send anything to your ear. Nothing left the fork and arrived at your eardrum. What actually happened is that the fork started vibrating, and that vibration caused a cascade of collisions between air molecules that eventually reached your ear. But here's the key insight that Feynman understood, the one that changes everything. The air molecules themselves barely move at all. Think about that for a second. You strike the fork on one side of the room. Someone hears it on the other side, 20 feet away. You think the air molecules traveled 20 feet. They didn't. Each individual molecule moved maybe a fraction of a millimeter, back and forth. That's it. So, how did the sound cross the room? Here's where you have to completely rebuild your intuition. Imagine a line of people standing shoulder to shoulder. I push the first person. They bump into the second person. Who bumps into the third? Who bumps into the fourth? The push travels down the line almost instantly, but the people themselves barely move. They don't walk down the line, they just nudge their neighbor. That's what's happening with air molecules. The tuning fork pushes on nearby air molecules. Those molecules bump into their neighbors. Who bump into their neighbors? Who bump into their neighbors? The push propagates through the crowd, but the crowd itself stays essentially in place. This is what Feynman meant when he talked about being operational. Don't ask what is sound. Ask what's actually moving. And the answer is almost nothing. The molecules jiggle in place. That jiggling propagates. That's it. But this should make you uncomfortable. If nothing is really traveling, what are we even talking about when we say sound? We're talking about a pattern, a disturbance. The same way a wave can move across the ocean, even though the water itself just goes up and down. The wave shape moves, but the water doesn't travel with it. Throw a rock in a pond. Ripples spread out in circles. But the water at the center doesn't rush to the edge. It just moves up, then down. The pattern travels. The medium stays put. This changes everything about how you think about sound. Pick up your phone. Someone calls you. You hear their voice. What are you actually hearing? You're not hearing their voice. You're hearing your air molecules vibrating in a pattern that matches how their air molecules were vibrating a split second ago. The pattern was transmitted. The air was not. Here's where it gets stranger. Feynman realized that this has profound implications for what sound actually is. Sound is not a thing. It's not a substance. Sound is a mechanical disturbance propagating through a medium by means of local collisions. And that means something critical. Sound cannot exist without a medium. Take away the air, and sound stops. Completely. Not because sound is weak, not because it can't travel far, because sound is fundamentally a pattern of molecular collisions. No molecules, no collisions, no collisions, no sound. This is why there's no sound in space. Everyone knows this, but most people don't know why. They think space is too big, or sound is too weak. Wrong. Sound cannot propagate through vacuum because there's nothing to collide. The pattern has no medium to move through. It's not that sound travels badly in space. It's that the concept of sound becomes meaningless. Feynman loved this kind of precision. He hated it when people said vague things like sound travels through air, because that phrasing hides what's really happening. It makes it sound like sound is a thing that moves. It's not. Sound is what we call it when molecules push each other in an organized way. Let's make this concrete. Strike that tuning fork again. What happens at the molecular level? The fork vibrates. Let's say 440 times per second. That's an A note. Every time the fork moves forward, it compresses the air molecules in front of it, squeezes them together, creates a region of high pressure. Then the fork swings back. The air expands, creates a region of low pressure. Forward, backward, 440 times per second. Now, those compressed regions don't just sit there. The molecules in the compressed region are closer together than they want to be. They're pushing against each other harder than normal. So they push outward. They bump into their neighbors, creating a new compressed region next to the first one, while the first region expands back to normal pressure. This compression travels outward, not because molecules are flowing outward, but because each compressed region creates the next compressed region by pushing on its neighbors. It's like a chain reaction of nudges. And here's the thing Feynman would emphasize. You can measure this. You can put pressure sensors at different distances from the tuning fork and watch the compression wave arrive. You can measure the speed. In air at room temperature, sound travels at about 343 meters per second. That's how fast the pattern of compressions propagates, not how fast the molecules move. The molecules are just jiggling in place at maybe a millimeter per second. This brings us to something most people never think about. The speed of sound is not a property of sound. It's a property of the medium. Change the medium, change the speed. Sound travels faster in water than in air, much faster, about 1,500 meters per second. Why? Because water molecules are closer together. They're already touching. So when you compress one region, it pushes on the next region almost immediately. Less delay between collisions. Sound travels even faster in steel, about 5,000 meters per second. Same reason. The molecules in steel are packed tight and held in place by strong electromagnetic forces. Compression propagates very quickly. Feynman showed us how to think about this. The speed of sound in a material depends on two things: how stiff the material is and how dense it is. Stiffer materials transmit compressions faster because the molecules push back harder. Denser materials transmit compressions slower because the molecules are heavier and harder to accelerate. Steel is both stiff and dense, but the stiffness dominates, so sound is fast in steel. Now here's where we need to talk about what actually reaches your ear. Because I've been talking about compressions and expansions, but what you perceive as sound is something else entirely. Your eardrum is a membrane, thin piece of skin stretched tight. When a compression wave reaches your eardrum, the higher pressure on one side pushes the membrane inward. When a low pressure region arrives, the membrane moves outward. The membrane vibrates. That vibration gets transmitted through three tiny bones in your middle ear. They amplify it. Then it reaches your inner ear, where there are hair cells, literal cells with hair-like structures. The vibration causes these hairs to bend. When the hairs bend, they trigger electrical signals in your auditory nerve. Those signals go to your brain. Your brain interprets the pattern of signals as sound. So when you hear a tone, what's really happening? A tuning fork vibrates. That vibration causes air molecules to push each other in a pattern. That pattern propagates to your ear. Your eardrum vibrates in response. That vibration gets amplified and transmitted to hair cells. The hair cells send electrical signals to your brain. Your brain constructs the sensation you call sound. Sound doesn't travel. A pattern propagates through collisions, gets detected by a membrane, gets converted to mechanical motion, gets converted to electrical signals, and finally gets interpreted by your brain as an auditory experience. This is what Feynman understood. There is no sound out there in the world. There are only molecules colliding in patterns. Sound is what your brain creates when it receives certain electrical signals from your auditory nerve. The external reality is just pressure waves. The internal experience is sound. This should completely change how you think about music. When you listen to an orchestra, you're not receiving the music. The music doesn't exist between the instruments and your ear. What exists is a complex pattern of air pressure variations. Your brain takes that pattern and constructs the experience of music. Different instruments create different patterns. A violin creates a certain pattern of compressions. A trumpet creates a different pattern. Your brain learned to distinguish these patterns, to categorize them, to recognize them as different instruments. And when multiple instruments play together, the patterns combine. The compressions from different sources add together. This is superposition. The air doesn't care where the compression came from. It just responds to the total pressure at each point. So complex patterns from multiple sources combine into a single, more complex pattern. And your brain somehow untangles that single pattern into separate sources, into separate instruments. That's extraordinary. Feynman loved examples like this because they show the connection between simple physics and complex phenomena. The basic mechanism is dead simple. Molecules push neighbors. But from that simple mechanism, you get all of music, all of speech, all of communication through sound. Let's talk about pitch, because this reveals something beautiful about the mathematics. When I said the tuning fork vibrates 440 times per second, that number has meaning. It's the frequency. Higher frequency means higher pitch. A fork vibrating 880 times per second produces a note 1 octave higher. Same note name, just higher. Why? Because 880 is exactly twice 440. And when you double the frequency, you go up 1 octave. This is not arbitrary. This is mathematical structure in nature. The pattern of compressions arriving at your ear repeats 880 times per second instead of 440 times per second. Your brain perceives that as a higher pitch, but recognizes it as the same note. This is why music works. This is why certain combinations of frequencies sound consonant and others sound dissonant. When frequencies are in simple ratios like 2 to 1, or 3 to 2, or 4 to 3, the patterns align in regular ways. Your brain likes that. When frequencies are in complex ratios like 17, 16, the patterns create irregular beating. Your brain finds that uncomfortable. Feynman would say, "This isn't mystical. This isn't about human preference. This is about pattern matching in neural circuits. Your auditory system evolved to detect patterns. Simple ratios create simple patterns. Complex ratios create complex, irregular patterns. The physics determines what patterns are simple. Your biology determines that you prefer simple patterns." Now, here's something that should break your brain. I've been talking about sound as compressions and expansions of air. But why does compression travel as a wave? Why doesn't the compressed region just stay compressed? The answer comes back to forces. When you compress air, you're pushing molecules closer together. But molecules don't want to be close together. They repel each other. Electromagnetic forces. The same forces that keep you from falling through your chair. When you squeeze air molecules together, those repulsive forces push back, hard. So, a compressed region immediately starts expanding. The molecules push outward. But they don't just expand back to equilibrium. They overshoot. They create a low-pressure region. Then the surrounding air pushes inward to fill the low-pressure region, and it overshoots, creating another compressed region. The air oscillates, back and forth, compression, expansion, compression, expansion. That oscillation propagates outward as a wave, not because anything is flowing, but because the pattern of oscillation triggers the same oscillation in neighboring regions. This is what a wave is. It's a self-sustaining pattern of oscillation that propagates through a medium. The medium provides the restoring force that causes oscillation. And the coupling between neighboring parts of the medium allows the oscillation to spread. Feynman explained waves this way. Every wave phenomenon, whether it's sound or water or light, involves something that can oscillate and something that couples the oscillations. For sound in air, the oscillation is compression and expansion. The coupling is the pressure forces between neighboring air molecules. Change the medium, change the wave properties. In water, the restoring force is gravity and pressure. In a guitar string, the restoring force is tension. In light, well, that's where things get really strange. Because light is a wave, but it's not a mechanical wave. There's no medium. Nothing is oscillating. We'll come back to that. But for sound, the mechanism is purely mechanical. Molecules pushing molecules. And that means you can trace every sound you hear back to something vibrating. Your vocal cords vibrate when you speak. A drum membrane vibrates when you hit it. A guitar string vibrates when you pluck it. That vibration creates the initial disturbance. The pattern propagates. Your ear detects it. Here's what Feynman would want you to understand. When someone explains sound by saying sound waves travel through air, they're not wrong exactly, but they're using language that obscures the mechanism. Waves don't travel the way objects travel. A wave is a pattern. Patterns can propagate without anything actually moving from place to place. This is the difference between transportation and propagation. Transportation means something physically moves from A to B. Propagation means a pattern or disturbance moves from A to B, but the medium stays in place. Sound propagates. It does not transport. Think about what that means. Every word you've ever heard, every piece of music, every voice, every noise, none of it traveled to you. What traveled was a pattern of molecular collisions. The molecules stayed roughly where they were. They just jiggled. And somehow, from that jiggling, your brain constructs the rich auditory world you experience. This is the beauty of physics. The underlying mechanism is simple, almost absurdly simple. Molecules push neighbors. That's it. But from that simple mechanism emerges everything. Speech, music, warning calls, thunder, the whole acoustic universe. And this is what Feynman discovered, or rather, what Feynman made clear. When you really understand sound, when you strip away the vague language and get to the operational reality, you see that sound is not a thing that travels. Sound is a pattern of pressure oscillations propagating through a medium by means of local elastic forces. That's not poetic, that's not comfortable, but it's true, and once you see it, you can't unsee it. Every time you hear something, you know what's really happening. Molecules colliding, patterns propagating, your eardrum vibrating, your brain interpreting. Not waves traveling, not sound moving. Pattern propagation through local interactions. That's the real story of sound. Not comfort, not familiarity, truth,